Hello and welcome to my channel. In this physics video tutorials, we are going to discuss elasticity. Alright, it is very important that you understand that whenever force is applied to materials, they tend to generally deform the material. Alright, material differs in nature, and as a result of these differences, they respond differently when force is applied to them. Another factor to look into when considering the responses or the deformation of materials is the type of force applied to them. But before we go into the relationship between the force applied and the resultant deformation, let's look into elasticity. What exactly is this elasticity? This word is a Greek word. This elasticity is a Greek word, and it means ductible. When we hear of the word elasticity, then we are talking about ductible. All right, but then it has a definition. What exactly is this definition? Let's put it down. Elasticity is the property of a solid material to return to its original size and shape after undergoing stretching. So this is what the definition of elasticity is: the property of a solid material to return to its size and shape after undergoing stretching, or when it has been returned to its original size and shape. So we have examples of this elastic material. One is the one we call rubber band. If you've heard of rubber band, it is an example of elastic material. If you've heard of catapult, it is an example. We have another one called the spiral spring. We even have the one we call balloon, and etc. There are many. So these materials I've listed, they are elastic materials. All right. So there are a lot of things we're going to discuss using either this catapult or rubber band or spiral spring or balloon or any of the elastic material to demonstrate. But before that, there's a man called Robert Hooke. He propounded a law, and then he named it after his name, which is Hooke's law. So let's look into the law holistically. What exactly is this Hooke's law? Hooke's law states that the extension produced is directly proportional to the applied force. You can take it down. The extension produced is directly proportional to the applied force, provided the elastic limit is not exceeded. So mathematically, we have F directly proportional to E, provided the elastic limit is not exceeded. So we can be able to tweak this expression or this equation one in such a way that we can be able to make out good sense of it. First, if we change the sign of proportionality, we can introduce a constant sign, which is K, all right, multiplied by this E. So what exactly is this F? F is the force applied, and F is measured in Newton. This force applied is measured in Newton. The SI unit of this force is in Newton. Again, this E, which is the extension produced, is represent extension, and the unit of this extension is in meters. And then what exactly is this K? This K is a constant of proportionality. It is a constant of proportionality and is called the coefficient of stiffness. The coefficient of stiffness. That's exactly what this K is all about. But then we can also make E or K the subject of the relation. How can we achieve that? If we want to make this E the subject of the relation, we've got to divide both sides by K, and that will result to F all over K. You can make this equation 3 if you like. Again, you can also make this K the subject of the relation, and that would be F all over E. And this will bring a unit for this K. So when we ask what exactly is the SI unit for K, of course, you know that force is measured in Newton and extension is measured in meters. So K is the unit for K is Newton per meter. Please take note of this. This is very important. All right. So the next thing we're going to talk about is the graphical representation of this. How do we represent this graphically? Now, if we have a Cartesian coordinate of this form, and then we have the vertical and the horizontal line. Say we want to plot the graph of load over extension. We want to see the representation of this, of the graphing of this particular material. So how do we achieve this? This is the horizontal plane and this is the vertical. If we have a straight line graph from the origin, let me do some sketching. A straight line graph from the origin. What exactly happened at this point? This point is where we call the proportionality limit. We term it as P. And then let's say we have some sort of move like this, and then break it down to this point. All right, I think this looks a bit good. So from this point we have another one here, another point here. We call this point Y. We can also call this particular point E, and then we can call this particular point B. All right, so what exactly are these symbols? The P is standing for proportionality limit. Proportionality limit. This essentially means that if you pull the rubber band and then to a certain position, or if you applied some sort of force on this rubber band, the rubber band we've mentioned earlier, or catapult, you can remember when you drag this or when you pull it and then release it, it comes back to its original shape and size without being deformed. So that particular position is what we call the proportionality limit. That's the straight line you're seeing. But from this point to this point is the yield point, and this yield point is the point beyond the proportionality limit. You can just have those short definition for these things. Yield point is the point beyond the proportionality limit. What exactly is the E? E is the elastic limit. E is the elastic limit. This is the point beyond the yield point. And finally, B is the breaking point. B is the breaking point. I think from this point Y to point B, the material becomes plastic at that point. So B here is the breaking point, or that is the point called the rupture. When the material breaks, if you drag the rubber band to the point where it has lost its elasticity, what happens to it? It will cut. That is the breaking point. All right, so we've demonstrated using Hooke's law of elasticity, and we have seen the relation, the mathematical relation of Hooke's law. But let's talk about another important parameters, which is called the Young's modulus. What essentially or exactly is this Young's modulus? Young's modulus. Apart from Young's modulus, we have other ones, which is the bulk modulus, the shear modulus, the shear stress, and all that. But then let's pay attention to Young's modulus in this video. What is Young's modulus? Young's modulus is represented by E. In some cases, you can use Y to symbolize Young's modulus. It is the ratio of tensile stress. Young's modulus is the ratio of tensile stress. Is the ratio of tensile stress to tensile strain. So you can say stress over strain. That is what Young's modulus is. But we can't go further if we don't know what this stress is all about and what this strain is all about. Symbolically, you can put this one as y equal to, this is how we represent stress in most cases. Just put it like this. And of course, that of the strain, a lot of materials or books have different way they represent that of the strain, but it's not a problem if you could just leave it as something like this that looks like an epsilon, all right, in representing this strain. However, if you want to keep it as stress over strain, there's no problem about that. So what is the next thing we need to do at this point? We need to define stress. What exactly is stress? Stress is the ratio of force per unit area. So we can put it as F over A. So if stress is force over A, what exactly is the unit of stress? Since force is measured in Newton and area is a meter square, therefore stress is measured in Newton per meter square. All right, so that's very important. For those of you also who would be asking, what about kilogram and all of that, the force unit that has to do with kilogram, that is a derivative from force, the definition of force to be mass times acceleration, where mass is in kilogram, acceleration is meter per second square. So if you use this to represent this Newton, then you can be able to play around with these meters so that you can be able to get another unit for this stress, and that is very simple. All right, so what about the strain? Strain is the extension produced per unit length, and extension is measured in meters, and of course symbolically you can have it as E over L. Extension is in meters and length is also in meters. So meter can also cancel out with meters. That means strain has no unit, and because it has no unit, it can also be called a dimensionless quantity because it does not have units, so it doesn't have dimension. All right, so having understood the definition of stress and strain that has to do with Young's modulus, let's represent this expression in the formula of Young's modulus. So how are we going to achieve that? It's simple. At this point, Young's modulus y is equal to, what is our stress? Our stress is force over area, and this is dividing what is our strain, that is E over L, extension all over load. We can play around this using division law or fraction. So if we have F over A, this is the same thing as dividing F over A dividing E over L. All right, so if you play around with this, it's more like saying y is equal to, by the time you tweak this by changing the definition, the division sign, you have to invert the term. If you change this sign to this, you invert the term after division sign, which is L over E. So therefore y is equal to FL over AE. So this will bring us to the unit of Young's modulus. This force is in meters, force is in Newton, force is in Newton multiplied by length, which is in meters, all over area is in meter square multiplied by this extension, which is in meters. If this meter cancel out with this meter, what is left is Newton per meter square, which is the same unit we had for stress. So Young's modulus and stress is the same unit. If you could remember, pressure is also talking about force over area. So essentially we are talking about stress is talking about the pressure acting on that material, because this pressure has a unit of force is in Newton and area is in meter square. So it's the same thing with stress and same thing with Young's modulus. All of this makes a lot of sense to you. So in light of this, let's solve 2 to 3 problems to demonstrate our understanding about elasticity. So let's see the first problem we're going to look into, and then we have to analyze it. So this is the first problem we're having. This question says this, that I meant to calculate the force applied in releasing a stone from a catapult if its rubber is being stretched through 5 centimeters and its force constant is 900 Newton per meter. So what are we going to do at this particular point? We're going to fetch out this parameter. The way I like for students to solve physics is, firstly, you bring out the necessary parameter mentioned in that problem, and when you're done doing that, then there you go, and be able to get the results of what you're looking for. In the question, what is mentioned? Firstly, we are asked to calculate for the force. So force is not given. You have question mark like this. What again do we ask to look for? Nothing. Parameters are given. We have 5 centimeters. What exactly is the 5 centimeters is for the extension. You've seen stretch, being stretched through 5 centimeters. That is the extension, 5 centimeters. But I would like for us to convert this 5 centimeters to meters. And the only way you can do that is to multiply 5 by 10 to the power of minus 2. And then you put it in meters. Alright. So the next thing we're going to look into is another parameter given, which is the constant, the force constant. That is talking about K, and that value there we have is 900 Newton per meter. So what do we need to do? We just remember the formula that link these two things together. Of course, when we talked about Hooke's law, we introduced a formula that F is equal to KE. Alright, so at this point we're looking for F. So what do we need to do? F at this point will be equal to 900, which is the value for K, multiply by 10 to the power of 2, or 5 times 10 to the power of minus 2. Alright, you can also write it as 5 times 10 to the power of minus 2. So let's use the calculator to work on this. Of course, we know that 9 multiplied by 5 is 45. And then we have 2 0 here. If you take it to 10 to the power of 2, 10 to the power of 2 multiplied 10 to the power of minus 2 will go out. So we just have 45 Newton without even bothering the calculator. So that is the solution for this first problem. I hope this is simple. So let's see another problem that also talks about this elasticity, and let's see what happened. Here in this problem, we say that a force of 35 Newton applied to an elastic spring 7 meters long. Extend it by 0.08 meters. Calculate the work done in extending the spring if the elastic limit is not exceeded. That will also make me to introduce the work done by elastic material. I think that skipped my memory, but with this problem I will be able to introduce that to you. Alright, but the first thing I said you must do after writing solution is to fetch out the parameters given in the problems. We have force given as what? 35 Newton. How do I know that is 35 Newton? Because it is, apart from the fact that force is mentioned, I've seen the unit there to be 35. Alright, the next thing given there is the length. The length is given as 7 meters. Of course, you've seen it here. Elastic spring 7 meter long. That is talking about the length. Right, next thing is extension given there in that question. You see, extend it by 0.08 we have 0.08 meters. All right, so now we are asked to calculate for the work done. How do we get this work done? Of course, work done is not the type you've done in work energy and power. Work done in elasticity is talking about half of k e square. Is derivable, but just take note of this expression that work done in elastic spring is half k e squared. But remember that when we introduced Hooke's law, we made this an equation that k is equal to F over E. I hope you remember when we said that F is equal to Ke, we made K the subject of the formula. So in that regard, we can substitute these values in for this. So we'll be having 35 divided by 0.08. Therefore, we have K to be equal to, let's use this calculator to get this value. So what we have is 437.5, 437.5, and the unit is what? Of course, it is Newton per meter, as earlier discussed. So then let's substitute this value. Why we are even looking for this case, because we need it for this work done that we're asked to find in this problem. All right, we're asked to calculate for the work done. Calculate the work done. So that's why we needed this value of K, so that we can substitute it into the formula. So work done is equal to, the formula is half multiplied by the value of K, which is 43 or 4,307. All right, is that 4,300? No, that is 437.5 times, what is the next value we have? Is extension, but we see square there. That means we have 0.08 all squared because of this square we are having in this formula. So W at this point will be equals, so what do we need to do? Let's use our calculator to punch this. Please make sure you punch carefully. So what I have is 1.3984. what is the unit for work? That's joules. So we can take this value approximately to be 1.4 joules. All right, you can see how simple this could be. So let's look at the last problem, and after which we can round this section up. So the next question we are having is this. We have to, it is said that the circular copper rod with a diameter of 3.5 centimeter and a length of 0.950 meters is subjected to a tensile force with magnitude 4,000 Newton. Calculate the tensile stress of the rod. That looks a bit simple, so let's see the solution to this problem, but this will be a bit technical. All right, so let's fetch out the parameter. We made there's something important that we're having here. Diameter is mentioned, so we say D. Let's use D to symbolize diameter, and the value given there is 3.5 centimeter. So we want to convert it from centimeter to meters, and that way we have 3.5 times 10 to the power of minus 2 meters. What is another essential parameter that is listed there? We have the length. From the question, we have the length to be 0.950 meters. All right, the next parameter we're having there mentioned is the force. The force, we have the magnitude of the force to be 4,000 Newton. 4,000 Newton. So what exactly is the major concern? We're asked to find the stress. The stress by formula is force over area from the basic work we've done, but we need to know the area from the question, a circular copper rod. So we need to know the area of a circular copper rod, so that way we'll be able to substitute it into this expression. So quickly we have this expression to become, we revamp this expression so that it becomes force all over. The area of that circular copper rod will be pi d squared over 4. So at this point, stress will be equals what is the force given in the problem. Of course, you can tweak this in a way that, because we are having this particular force, you can take it up, you can play with it using fraction. So this is the same thing as 4f all over pi d squared. So it makes it more easier for us. So we have this point to be 4 times, the force is 4,000 divided by, what is pi? Pi originally is 22 over 7, which is 3.142. But even if you put it as pi here, we know that the value is 3.142 approximately. That will multiply by the value of the diameter that has been given. What is the value of the diameter in the problem? Is 3.5. And then we put it in this standard form. So here we have 3.5 times 10 to the power of minus 2, but this time we have to square it. Why are we squaring it? Is because the diameter is squared. So what do you think is the solution? For those of you who know how to punch calculator, let me see how you can be able to put in things together and get this answer for stress. Let me know in the comment section what your answer is. And if you've not subscribed to my YouTube channel, please hit the subscribe button, turn on the notification bell, and also make sure you share this video